Alright, so this is another example, and then again we are trying to find the stresses at position. We are trying to find Rn and the stresses at position A and B. Right? Okay. So now we get at it. So in order to find Rn, which we said earlier, is based on the loading system and the geometry. Right? We said the general formula ends up of this way: A on B, right? And then we have length function. We have Rho, Ri, right? But then when you look at this particular figure, when you look at the cross section, this one right here, you get to see that you can't find it directly, right? If you try to do it straightforward, it's much more easier if you take the cross section in parts and then do it. So we end up using this formula instead, just a summation. Don't later we introduce a summation to do it part by part. So let's say we have this one here, this one we call a stem, this one is a flange, right? Engineering terms. So the part, just to find out Rn, right? This is 1, which is the stem, and this is 2, we call the flange, right? In order to find Rn, what do we need? We just need A of each part, and then we need so we need A, we need B, right? We need B, and then we need Ro and then Ri, right? Ro and then Ri, and then we will need the sum of them. So let's see. Okay. Let's see. Okay. So then Ri, what else do we need? We can do the sum of the A about here. Right? So the summation will come somewhere here. Right? So you can do the sum of the A here. We'll need the sum of the B length on that side. So in order to do that, we need the product of them. We need B length of Ro on Ri. Right? We need that as well, and we get the product, and we get the sum of it, right? We have to find out our Rn. So this right here is the formula for Rn that we are using, right? And now that we've named the part, stem and flange 1 and 2, right? Let's move on. We start with the stem, right? What's the area? The area will be the 15. Let's open up. The area will be the 15. This 15 times the 70, right? What is that giving us? 15 times 70. That gives us 1050 for the area of the stem. The unit is very important. Mm squared. The B, looking at it, because we end up with let's just move on. Mm here. Our R naught is mm. Our I is mm. And this right here will end up being just mm. Why so? This one here, this mm on mm cancels out, we end up getting only mm. So mm squared on m, that gives us just mm for the Rn, right? So that's it. Unit is very important. So the B for the stem. Then again, what do you say about the B? We said the B is just the thickness, right? Just this thickness here. So for the stem, the thickness is what? 15, right? And then now we are trying to get the RO, right? The RO is from the center of curvature to the outermost fiber of that particular section. So this right here is I, right? And the starts are here, and the whole thing, this radius here is from here to here, right? So let's start from the center of curvature. So we are assuming the center of curvature is about here, from here to here. right? That's how it moves, just as this one is moving, right? So if you are trying to find r not just from the center of curvature to the ri where its first fiber is, right? And to get that, what do we need? We need this from here to here, right? Do we have the distance for that one? So since our focus is on the stem here, which is the one that we're talking about here, right? If we're trying to find the RO, the outermost fiber will be this side, B, right? So that'll be moving from the center of curvature throughout to this very end. And to get that is this 85, right? Plus the 20 here, plus the 70, right? So let's see what we get for that. Let's see what we get for that one. Okay. So we're trying to get the R naught for the stem, which is the part I, right? The part 1, right? So let's see. So as we were saying, in order to get that, we need the outermost fiber of the part 1 is just from the center of curvature here up to this side here. So to do that, we need from here to here, which is 85, and then we need this thickness here, which is the 20, right? And then what we need plus the 70 here, right? That gives us 175, right? And for the RI, we are trying to find the RI here. So let's see. The RI will just be from here, because you're on part 1 to this side, right? To do that, that will be the 85, right? Plus this here, which is the 20, right? So that will give us 105, right? 105, right? And then now we move on to part 2. So now we are done with this part 1, which is the stem. Now move on to the flange, right? To the flange. Now we are on this one. For the flange, the area will be the 50 by 20, right? 50 by 20. That gives us 1,000, right? 1,000, right? And the B of that one, we know we are saying is the thickness of it. For the flange, we have it to be 50, right? Right. What's the RO? The RO will mean from this center of curvature here up to this outermost shell here. So that will be the 85 plus the 20. That will be the 105 again. 105. And the inner will be just from here to here, right? That will be 85. 5. Now we just need to find this one right here, right? So let's see. Okay, so that's our form B. We have len outer. Let's represent that with y and then x, right? Okay, so I'm trying to find for part 1. Our B here 15. Our y, which is outer, is 175, and then our x, which is our inner, is 105. So that gives us this 7 point something. That's 7. Sorry. That gives us this one here, 7.6624, right? Now I move on to the same for the flange. So let's see. Our B here is 50. Our X, which is the outer, is 105. And our inner is 85. And that gives us 10.565. Adding this gives us 7.6624, and that gives us about 18.2279, right? And the area gives us about 2050, right? Yeah. All right. End up having an Rn of 2275, and that gives us 112.4. Let's write it somewhere. Our Rn will be 112.4674 mm, right? So this is what we have for our Rn. And the next thing for us to find is to find stresses at A and B, right? Bending stresses. To find that, let's write out the formula. Let's see. So we know the bending stress at a particular position is minus the moment, right? And then we have Rn minus R all on R A to bracket RC minus Rn, right? Okay. So if we are trying to find it at the stress at A, bending stress at A, which we don't know, what we need, M will be the same throughout, right? So we'll have our M. What do we have for M? Our M is 2700 Newton meter, right? So that's 2700 Newton meter, right? And then what do you have for Rn? Now we found Rn, right? We have that to be 112, and then we have our Rn already. That's 112.4674 mm. Our R at A, our R, right? Oh, let me look at it again. At A, our R will be the same as this 85 here, right? So our R is kind of like RE is like 85 mm, right? And our area, the area here in this case is the total area, right? That's 2050 mm squared. Mm squared, right? And our RC, okay, we'll come back to that. Have our iron already, RC. And in this case, because it's a complex figure, we go about a particular way to find our RC, right? Which we said earlier to be this. Sum of the area, right? Times the RI for each part, all on the area, right? So the product of this is a sum. So let's go back to this one right here. Let's try and add the table, a part to this table. Okay, let's see. This one here. So it's even good that when you start, you know what you're trying to find. That way, you write out all the equations that you need, and then if it's a table that you're supposed to do, you do that. It makes your work easier. Yeah, makes the work easier. So now I have this. Okay, I have all this. Oh, there's a shifting table. Let's do it here. Let's do it here. Let's do it here. So if I have a flange, let's see, stem, which is part 1, right, and I have, there's a part, and our flange, which is the 2, right? All I need is their area, right? And then I need their individual radius, and I need a product of them as well. And then I'll get a summation here for this, and then for this. So this one here is R, C of each, and then area, right? So that's what I need. For the stem, we have the area already to be 1050. For the flange, we have it to be 1000. And then I will come to the RC, right? So for the stem, if you're trying to get to the center of it, this is what we do. We'll have to move completely from the center of curvature. Let's look at the wall. From the center of curvature, which let's see about here, we move completely across the flange, right? Which is 85 plus the 20, that's 105, to the plus 70, half of it, right? So that's 85 plus 20 plus half of the 70, right? And that gives us 140 for the stem, right? For the RC, 140 to the center of the stem, right? And for the center of the flange, which is the part 2, we just move 85, right? Move 85 plus half of it, which is 20 on 2, right? And that gives us 95, right? That's 95 here. So now we just need a product. So 1050 times 140, that's 147,000, and this is in mm squared, this is in mm, and this is in mm cube, right? Okay, and for the flange, that's 1000. That gives us 95. How many zeros? 1, 2, 3. Add in this 95, 1, 2, 3 plus 95, 1, 2, 3 plus 147, 1, 2, 3, and that gives us 242, 1, 2, 3, right? For the area, that's 2000, 2050. Right. So we end up getting our RC to be 242,123 on 2050. So let's see. 242,123 on 147. Sorry, on 2050, and that gives us 1180. That's our RC, right? Something missing. Let's see. It shouldn't be that huge. Okay, let's see. Let's do it. 1050 times 140, 3 zeros, right? And then 95 times 1, 2, 3, 3 zeros, right? That's plus, so 95, 1, 2, 3 plus 147, 1, 2, 3, 242, 3 zeros, right? All on the area, right? So this That's 242.123 divided by 2050. Yeah, so that gives us 118.0488 about this right? So now that we have all that we need to find the stress at a point A, right? We just look at the unit. Everything here is having the unit to be mm. The only thing having it in m is the moment, right? So that will give us 2700 times 10 to the power 3 Newton millimeter, right? So this is what we have. Okay, so we move on to find the stress at A. So stress at A give us minus, the moment is 2700 10 to the power 3 10 to the power 3. Our Rn is 112.46, and then our R, right, for when we're trying to find the stress at bending stress at E, that's 85, right? And you have 85, right, times the area we know to be 2050, and then RC, which we found to be 118.05, and then Rn is 112.46 something. We'll put that in when we're trying to punch it. On to 0.46. So let's see what we have for bending stress at A. Minus 2700 times 10 power 3 112.4, that's for Rn. There's Rn 4674 minus R, which you have to be 85. Minus Rm 2700 10 power 3 brackets. What do you have for Rn? That's 112.4674 minus R, because we're trying to find the stress at A. R is what is it? 85, right? And we have our R here again, 85 times the area 2050 brackets, and then our RC, which we found to be 118.0488, and then we have Rn, which is 112.4674, right? And what are we getting? This is what we're getting for the stress at A, minus 76.2545 megapascal, because everything is mm. Then because of this negative here, it means it's under compression, right? And you can look at it and then actually see the physics behind that. At E, there's it. At E, the moment is this way, right? So that side, the fiber at that side tend up to be in compression, right? It's being compressed at that side, right? So if we try to find at B, the stress at B, let's see what that will be. So the same equation, stress minus M, and then we have Rn minus R, all on RA to bracket RC minus RN, right? So if you're trying to find the stress at B, the only thing that's changing, everything else is constant. The only thing that's changing is the R, right? And at B, we have this R to be from here to here. So we're adding everything up. That's 85 plus 20 plus 20 plus 70, right? That's at B. 85 plus 20 plus 70, that gives us 175. So our R, which is the same as something like RB, is 175 mm, right? So we have all that we need. So our stress at B will be minus 2700 10 power 3, right? Rn is not changing, that's 11246. R is the only thing changing. Now we have it to be 175 times 2050. Our area not changing, RC not changing, that's 118.05, and then our Rn not changing, 112.46. So let's see what we get for this. Okay, minus 2700 times 10 power 3 brackets. Then we have 112.4674, right? That's 74 minus, yeah, 175 all on 175 times 2050 brackets, 118.05, that's for RC, 0.0488 minus Rn, which we have, what is it, Rn, 112.4674. Okay, and that will give us our stress at B. Let's see if we're pointing the right thing. Okay, so that's about it. This will give us 84, because we've used everything is in millimeters, right? All the length unit is in millimeters. That's 320 about 9 megapascal. And because there's positive here, it means it's actually in tension. So we look at the diagram or the system to see what's actually happening at B, right? So our interests were here and here, right? You see this side here is actually being compressed by the moment, right? So negative, we had a compression there, and our B is actually being stressed, right? This side is being stressed, that's why it's tension there. All right, so that's it for this example as well.